Okay, so this is 15.8 Lagrange multipliers. And this is going to be a technique that allows us to do optimization on regions which are a bit hard to work with compared to what we talked about in the last section. All right, so this is actually maybe even one of the newest, the first new thing that that we're learning in this class. Everything else, maybe in the past sections, have always had, in a way, good analogies to one variable calculus. But even the problem here is something that you don't really encounter in one variable calculus. All right, so what are we trying to do? So we have a function, and let's introduce this with two variables. But of course, as usual, this technique works for any number of variables. All right, so we have a two-variable function. Let me draw the domain. So here's our domain, right? So in the last section, a typical problem was to find the maximum of f of x comma y, or minimum, over a region in the domain, right? So maybe we're only interested, so the examples we did last time, we looked at a couple of triangles, right? So maybe we're interested in this region, right? And we wanted to find the maximum and minimum that f achieves in that shaded region. Okay, so the important thing, the important feature relevant to this section is that this region here, this shaded region, is two-dimensional, all right? In that, if you're standing in the region, right, you have two directions to move, okay? So, the problem we're going to address in this section is, again, two-variable calculus. We have our domain here again, but now we're not interested in a two-dimensional region. We're only interested in a one-dimensional region. So maybe something like that. All right. So I want to find the maximum and minimum that f achieves on this curve. Right? Not on the inside. I don't care about the inside of the curve. So I don't care about this blue shaded area. I don't care about this outside area. I only care about how f behaves on the curve. Okay? All right. We kind of addressed this in the last section, right? When we did the optimization in a full region, because when we looked at the boundary portion of the problem, so that would be this segment, and this segment, that's exactly the kind of problem that we're solving today, all right? So we already have one technique for doing these problems, which was parameterization, right? The way we solved these problems in 15.7 was to do parameterization. We parameterized this curve, we parameterized this curve, we parameterized this curve, and we did a one variable calculus optimization problem on each of those three curves, boundary curves. So now we're going to have a new technique where we don't have to parameterize, which is good because sometimes parameterization is not necessarily easy, which allows us to work with, so this allows us to work with a bigger variety of curves, all right? And in particular, it gives us a second technique for working with the boundaries, boundary portion of the kinds of problems we saw in 15.7, all right? Okay, but of course, they don't just appear as boundaries of 15.7 problems. They can appear just as problems of their own, right? So here's an example. So let's say we have a hill here, right? You're taking a drive on this hill, maybe a scenic loop drive. So perhaps here's the road, right? It loops around the hill or the mountain or whatever, right? So this is of course in space, right? We want to know what was for example, the highest and lowest points of elevation that we were at during this drive. Okay, so that's naturally going to be a Lagrange multiplier type problem, because we don't care about portions of this hill that are not on the road, right? We only care about the elevation that we felt while we were on the drive, okay? And we were just strictly restricted to the road, okay? So while the hill, for example, had its highest point right there, right? And if I look at where that is, let's say on a map, right, that would be down here. Maybe I should, I'm going to put the XY plane down here like this, in this form. All right, so think of it like a map, right? So the highest point of our hill is right there, right? But we literally don't care, right? We only care about this portion of the map, right? Which is the portion that lives directly below our road. All right. So where is the maximum and minimum of our function on this curve down here in the domain? That's the domain that we care about. Okay. All right. And as usual, if you have pictures, then the problems are always easy, right? You just take a look at this, and it looks like maybe that's going to be our highest elevation point, and looks like maybe that would be our lowest elevation point. All right, but as usual, in reality, you usually do not have pictures for your functions. And even if you did have pictures, you can't rely on them in terms of accuracy. So we're gonna have to work all these problems as usual in terms of formulas, the analytics. All right. Okay. By the way, I should say, so if this is the highest point, what we're looking for in this section is this point right there in the domain. All right. The coordinates in the XY plane where we're at our highest point, and down here this would be the coordinate in the XY plane where we're at our lowest point. All right, so that's what we want. That's what we want. This guy we don't want because it's not on the road, right? All right. So how do we do this? One way is to parameterize this curve. Right? Parameterize this curve down here and do it as a one variable calculus problem. But like we said, we would like to have another technique because parameterization sometimes is not easy. So the way we're going to think of this is, let me draw a picture again, just the road portion. So the way we're going to think of this is we're going to think about driving on this road, right? So if we are on this drive, let's say you're blindfolded and you can't see, right? So if you feel like the car is tilted upwards like this during your drive, right, then you know for sure you're not at a maximum or a minimum, right? Because if you can feel kind of tilting back into your seat, you know that, let's say, 1 second before you were at a lower altitude. So you're certainly not currently at a minimum, okay? You know that because, again, you're tilted forward, upwards. You're not at a maximum because 1 second from now, you're going to be at a higher point. Okay? So if you feel yourself kind of tilting upwards, right, or falling back in your seat, you know you're not at a maximum or a minimum. Okay? In the same way, if you're, again, blindfolded in your car and you feel that you're tilting downwards, or you're kind of leaning forwards or tilting downwards, I guess, you know that you're not at a maximum or minimum because, if you're kind of facing downwards in a way, then 1 second previous, you were at a higher point, right? So you're certainly right now not at a maximum, okay? 1 second from now, you're going to be at a lower point, so you're certainly not at a minimum, right? Because 1 second from now, you'll be even lower, right, in elevation. So we want to be looking for places where you feel like you're horizontal, all right? So if you feel like you're horizontal, then we can't do the same analysis, right? Just before you were horizontal, just after you're horizontal is not necessarily higher or lower, right? We can't make that kind of conclusion. So where you're horizontal, where you feel like you're horizontal, those are going to be your candidates for the max and mins. All right, so those are the equivalent of critical points for this problem. And in fact, if you do parameterize this curve down here and you do this problem via parameterization, these places where you're horizontal are literally exactly the critical points that you do find when you do the one variable problem. Okay, so the one good news is that this technique is going to be very different from what we've seen before, but ultimately the core of it is exactly the same idea. All right, we're looking for places where you're horizontal. Okay. All right, so now the question is, how do we determine where you're horizontal? Again, assuming that we do not have a parameterization. All right. Okay. Oh, I want to mention one thing. So when I say horizontal, I mean, of course, you're sitting in your car and you feel like you're horizontal as opposed to tilting up or down, right? Notice that one thing that doesn't matter is how this hill is tilting to your left or your right, all right? So you're horizontal right here in this picture, but if this is a hill, right, perhaps to your left, the hill is going upwards, and to your right, the hill is kind of falling downwards, right? That's irrelevant. We only care about how you feel, right, in your car as you're driving along the road, right? What's happening to your left, what's happening to your right is irrelevant. Okay, so this is in big contrast to the problems we talked about last time. Let's say, again, two variable calculus. We're interested in a region, right? Let's say this region here. We were very interested in all directions, right? We wanted to find where the gradient was 0, which meant we wanted to find where the derivative in the x direction was 0 and the derivative in the y direction was 0, right? Which ultimately means that the derivative in every direction is 0, okay? But here, the big difference in this problem is that we only care about the direction of motion, okay? So in terms of the picture downstairs, right, like on the map, we only care about, so if I'm at this point right here, we only care about that direction right there, all right? So the hill could be going upwards or downwards in this direction. It could be going upwards or downwards in that direction, right, perpendicular to our direction of motion. Completely irrelevant, all right? Which again, it totally makes sense when you think of this as a as kind of find the greatest elevation or find the lowest elevation type problem. Okay. All right. So immediately we realize that we can't solve the problem in the same way that we did in the last section, right? In the last section, to solve this problem, or the last section's point of view was we just solve for gradient f equals 0. Right? But that's not going to work here because this point right there, right, which looks like it could be the point of greatest elevation, it definitely does not have gradient f equals 0, right? Because again, we're on a hill, right? It's tilting upwards here, right? Maybe a hill like this. It's tilting upwards here, right? So the gradient in this particular picture, the gradient looks like it's in... the gradient looks like it's in maybe, oh, that didn't work. Sorry. The gradient looks like it's in that direction, and it's definitely not 0, right? So in other words, when you're driving at that point right there, if you look to the left out the window, you'll see the hill sloping upwards, right? And if the hill's sloping upwards to your left, that means the gradient is definitely not 0, all right? So gradient f equals 0, solving for that is not going to do it. All right, we don't need actually such a restrictive condition. We only need the derivative in the direction of motion to be 0. All right, we only need the derivative in the direction of this yellow arrow to be 0. Okay, so this is why we can't just do the same thing we did in 15.7. All right. Okay, so let me write a little bit of what I just said in math. So let me call the, let's say we're at a certain point on our road. Let's call the tangent direction u. Okay, so this is the direction of motion. So what we're looking for is we want directional derivative in the direction u of f to be 0. right? So we want, let me kind of be a little bit more precise. We want points, x comma y. So we're searching for points as usual, right? We want to find the locations in the xy plane where we get the highest or lowest elevation. So we want points x comma y where the directional derivative of f in the direction of motion at xy is equal to 0. All right. Okay, so we're going to start from here, and from this we're going to write down some equivalent conditions to the point where we actually get a kind of equation that we need to solve. All right. Okay, so we want points where d sub u f x comma y equals 0 and u is tangent to the curve. Okay, or tangent to the road in terms of my particular example. All right, let's see. Let me rewrite this condition. This is the same as, right, d sub u f x comma y equals 0 is the same as gradient f dot u is equal to 0. And again, this is for u tangent to the curve. Right? We're not interested in directions that are perpendicular to the curve or other directions. Again, all right? Okay, again, moving from this to this new step with the gradient, of course, as usual, we're assuming everything is differentiable and all that. All right? Otherwise, again, you cannot make this step. Okay, so what does this mean? The dot product tells me about angles, and for the dot product of these two guys to be 0, that means we want points. So again, we're looking for points x comma y where this is true. All right. So that means we want to find points. So we want x comma y where gradient f at that point, at those points, is perpendicular to u. Okay. Again, the dot product being 0 means you're perpendicular. All right. And again, as usual, u is tangent to the curve. Okay, so how do we do this, right? So this is actually really good, right? At least this idea here, right? We have kind of a more concrete mathematical formulation of our problem, right? We're looking for points x comma y in our domain or on the curve, right? Where gradient f is perpendicular to our direction, to the tangent direction of the curve, okay? Or tangent to the direction of motion, if you think of this as a again, the driving problem. Okay, but the question is, how do we do this, right? Luckily for us, there's a trick here, and that's to represent the curve as a level curve. So to do this, to find these points, right? Again, the alternative we talked about last time was just to parameterize, right? And we effectively are doing exactly this when we parameterize and then solve the one variable calculus problem. But the new idea, the Lagrange multiplier idea, is to find these points, write the curve or the road as a level curve of some function. Okay, and then what we're going to do is we're going to exploit the fact that we understand level curves. All right. Okay, so what do I mean write the curve? By the curve, I mean this curve down here. All right, the curve in the domain that we're interested in, right? The picture of the road on our map. Okay, so we want to write this curve right there as a level curve of some function. It doesn't matter what function. Well, it matters a little bit. We'll get into that. But for now, let's just say it doesn't matter what function. We just want to find a function where this curve is a level curve of that function. All right. It could be, this curve could be the 10 level curve of that function. This curve could be the 20 level curve. It could be the 0 level curve. It doesn't matter as long as it's a level curve. Okay. So we'll certainly do an example of this right when we finish this, this discussion here. Okay, so a level curve of some function. So generally, I'm going to be calling, if we're working with the function f, I'm going to call this function g. And as usual, it's going to be a two-variable function, right? Because we need something to be, we need this curve to be a level curve, right? So it's of a function. So it has to be a function that has the same domain as f, right? And f takes two variables, so g should take two variables, all right? Okay, and again, notice very importantly that this problem, as stated in the very beginning of the problem, there is no function g. You are discovering this function g as a helper function to help you solve the problem. But it's, in a way, the g is not native to the problem, all right? It's just a kind of a tool that helps us pass through in order to solve the problem, all right? Okay, so as a level curve of some function g. Okay, so let's be, actually it doesn't matter what level curve, all right? 10 level curve, 0 level curve, doesn't matter. Okay, why does it not matter? Because I only care about this g in that I want to work with its gradient. Okay, so the important thing is we know that gradient g of x, gradient g is perpendicular to the curve. All right, that's the really important feature that we're going to exploit of our g, right? So remember, if you have a level curve, let me draw maybe the level curves of g, right? So this is happening in the xy plane, right? The domain of our function. So these are the level curves of g. Remember that, remember that gradient of g always points in the direction of, at any point, right? Always points in the direction of greatest increase. So in this picture, it would be either this way or the opposite direction. Okay, at that point, it looks like it would be either this way or the opposite direction. Okay, and in directions tangent to our level curve, we talked about this when we introduced level curves, or introduced the gradient. Gradient g is perpendicular. All right, so gradient g is perpendicular to this red arrow right there. All right, gradient g is perpendicular to that arrow right there. It's perpendicular to the curve. All right, that's kind of the shorthand way of saying it. Okay, well, what was it that we wanted? We wanted gradient f to be perpendicular to u. Well, u basically represents the curve, right? U is tangent to the curve. Okay, so what we have is we want, at this point, we want gradient f perpendicular to u, or I'm just going to write the curve, right? And we have gradient g is perpendicular to the curve. Okay. Well, what does that mean? That means that gradient f and gradient g have to be parallel. We're looking for x comma y, where gradient f is parallel to gradient g. Okay. All right. That's it. That's the core idea behind Lagrange multipliers. So how do we actually do this? Well, what does it mean for two vectors to be parallel? It means that one vector can be written in terms of the other vector, written as a constant times the other vector, right? If you're parallel, you're in the same direction, but you might have different lengths, and you might point in the opposite direction, right? But that's the only difference. So in other words, we're looking for points x comma y, where gradient f is equal to lambda gradient g, where lambda is a constant. Right? That's what it means to be parallel. The relationship to each other is that one is a scaling of the other vector, right? Okay. This is the key kind of formula that we're going to be working with, because now we actually have an equation that we have to solve, right? So all the way up here, for example, when we said we're looking for gradient f that's perpendicular to u or perpendicular to our tangent direction, we don't really have an equation there, right? Now we actually literally have an algebra equation that we know that if we solve it, we're going to get candidates for our maximum or minimum. Okay. All right. Before I actually write down the full technique, I have to make a couple notes here. So first note is we don't want. So I said before that any g will do, but not literally any g. We don't want gradient g equals 0 for any point on the curve. All right, because if gradient g is equal to 0 for a point on the curve, then it's going to completely mess up this equation here, right? Because this right-hand side is going to be 0, which means that we're only searching for points. Which means that at that particular point, we're only considering where gradient f is 0, where we actually have a full critical point, right? Which is not what we're looking for. Again, we only care about the direction tangent to the curve. Okay, so we want to make sure that when we fabricate this function g, its gradient should not be 0 for any point on the curve. Okay. All right. Technically, you can have gradient g equals 0 for points on the curve, but then you'd have to include them as candidates. All right. But it's better, for this kind of first try at Lagrange, or first look at Lagrange multipliers, let's just keep it like this, right? Find a g, make sure it does not, its gradient is not 0 on the curve. Okay. All right, the second point, we're solving for gradient f equals lambda gradient g. We're solving for points x, y, where this is true. Don't put the lambda in front of the gradient f. All right. So let me write not lambda gradient f equals gradient g. All right. Okay, seems like there is no difference. And most of the time, in a way, there is no difference, right? Because if, for example, if lambda up here in the equation that we actually want to work with, if lambda were 3, right, then I could just throw it to the other side. And I would get 1/3 of gradient f equals gradient g. So it seems like it's the same problem. But it's not, because there's the special case where lambda is 0, right? If lambda is 0, then, if lambda happens to be 0, then you're never going to be able to solve this situation here, right? Because when lambda is 0, you're going to be asking for gradient g to be 0. But if you follow the instructions from the first part here, gradient g is never 0, right? So you're going to miss a critical point. You're potentially going to miss a critical point if you put the lambda on the left side. If you put the lambda with the gradient f, all right? Most of the time, it's not going to happen. But if, in your particular problem, it happens to be that a solution includes lambda equals 0, you're going to miss that critical point. Okay? So the lambda has to go with the gradient g. All right? And again, that whole thing depends on the fact that we're requiring gradient g equals 0, not be 0, don't want, right, at any point on the curve. Okay. So ultimately, so those are my two small notes. So ultimately, our problem is, so just like in one variable calculus, you have a problem where you're solving f prime equals 0, and that ultimately is an algebra problem, right? You're solving an algebra equation. Last time in 15.7, you're ultimately solving an a system of algebra equations, right? F sub x equals 0, f sub y equals 0, f sub z equals 0 if you have a z, and so on, right? Here, ultimately, the problem is you want to solve gradient f equals lambda gradient g. But there's one more. You need, so here's the thing. If you only solve this first equation, you might get solutions which are not on your curve, all right? Because this equation here doesn't have anything to do with being on the curve or not. It's about tangent directions in a way, okay? So the first equation here has no relation to being on or off the curve. So you need the first equation here to kind of get the correct critical point in a way, but you need the second one to be on, so you need to make sure you're on the curve, Okay. And in terms of algebra, what does that mean? That means that you need to solve for x comma y so that the first equation is true, but also so that g at x comma y, so I'm going to put in the x comma y's here like this so they don't look too messy, right? You're looking for x comma y so that the first equation is true, but you also need g of x comma y to be equal to whatever level it was supposed to be, right? So if all the way up here when you were fabricating your g, when you were fabricating the curve of some function g, right? When you were fabricating this, your curve was supposed to be a level curve of g, right? If it's the 10 level curve, then down here, this constant needs to be 10, okay? If your curve is the 5 level curve, then this constant needs to be 5, all right? Again, in effect, you're making sure the second equation makes sure you're on the curve, okay? Because we don't care about, again, we don't care about, in this particular type of problem, we don't care about what's happening off the curve, all right? Okay, so how many equations, so as usual, when you're doing these kind of solving algebra, you want to know how many equations, how many unknowns there are, right? So how many equations are there here? Well, gradient f equals lambda gradient g. That means solving f sub x equals lambda g sub x. F sub y equals lambda g sub y, right? And again, this is for 2 variable. If it was 3 variable, f sub z equals lambda g sub z. All right, literally the same idea. It's not as easy to visualize, but it's the same idea. And to be on the curve, you need g to be equal to whatever constant that level was supposed to be at. All right, and again, all of this is x comma y. You're looking for the x comma y that makes these 3 equations true. Or yeah, makes these equations true. Okay, so one thing you notice here is you have in the previous section, we solved gradient f equals 0. That was just f sub x equals 0, f sub y equals 0. 2 equations, 2 unknowns, right? So at first glance, this looks like we have 2 unknowns, x and y, but we have 3 equations, which, the general principle is that there's not going to be any solutions. But the reality here is that there's actually 3 unknowns, right? So the unknowns are x, y, those are the 2 guys we actually are looking for, but also lambda, okay? So lambda is an unknown quantity, right? We don't know what it is. Ultimately, we don't care what it is because we're only looking for x and y, but very frequently we'll need to find lambda during the process of finding x and y because it is, again, unknown, all right? Notice, C is not unknown, because when we wrote g as a level curve, we had to know what c was, right? That c was 10 or that c was 5. All right, so c is not unknown. X, y, and lambda are your unknowns. Okay. All right, so we do have 3 equations and 3 unknowns. So generally, again, the general principle is that there's going to be a discrete set of solutions. So maybe a finite or a not too infinite set of solutions. All right. Regardless, we've reduced our problem from an infinite number of possibilities, right? The maximum or minimum, if we don't know anything, could be anywhere on the curve. But now we know the max or min has to be restricted to points that satisfy these 3 equations. All right. So that's a huge cutting down of the possibilities. Okay, let me draw a picture for what we're looking for, and then we'll do an actual concrete example. So in terms of the picture, let's say this is the curve that we're interested in, right? So this is a picture in the xy plane in the domain of my function, all right? Okay, so this is in the xy plane. This is the curve that we're interested in, this is like, in terms of the kind of driving and elevation idea, this would be like the curve on our map, all right, on Google Maps or something. The road on Google Maps. All right, so this would be a level curve of G, all right? Okay, I'm going to draw the level curves of F, all right? So this is a level curve of F. This is another level curve of F, another level curve of F, and so on, all right? Okay, and if you think of this as a hill, right, perhaps in this, for example, at this point there, you're at the highest point of the hill, and down here, you're at a lower point on the hill, okay? All right, so if you're looking at, for example, a topographical map with a road on it, right, this might be what the map looks like, right? The road being the red segment here. Okay, so what were we looking for in terms of our algebraic computations? We were looking for points x comma y, so points on this map, where gradient of f is parallel to gradient of g. All right, so gradient of f, for example, at this point, like I said, if this is a hill, then gradient of f would be perhaps pointing in towards the, I mean, for sure it's going to be pointing towards the steepest direction, right? So it's going to be perhaps like that, right? Here the gradient is going to look like that, right? Here the gradient is going to look like that, for example, right? Always perpendicular to the curve, okay? So these are my gradient f's, right? At various different points, okay? We want gradient f to be parallel to gradient g. So what's gradient g? Gradient g is, again, perpendicular to the curve, to the red curve, all right? So gradient g looks perhaps like this, right? And again, the actual direction of the arrow doesn't matter. The important thing is it's perpendicular to the red curve, okay? So I'm drawing it as pointing outwards, but in reality, it could be pointing inwards. That makes no difference. The difference would be in the lambda. The lambda might be, difference between a positive lambda and a negative lambda up here in this equation. Okay, so I want points where the two, where gradient f is parallel to gradient g. So in this picture, that would perhaps be here, for example, right? So gradient f would perhaps be pointing that way, like that. And gradient g, if I'm drawing it as I have been, is going to be pointing in that direction. Like that, right? They're parallel. Okay, one is negative of the other, right? Whereas, again, let's take a look at a point where that we're not looking for, right? So, for example, right there, right? At this point, let me erase this guy right there. So at this point right here, gradient g is pointing in that direction, right? Perpendicular to the red. Gradient g is in that direction, right? Whereas gradient f is in that direction, right? They're not parallel, so we're not looking for that point, okay? So we're looking for points, like I said, like this one right there, all right? So another one that's obvious in this picture is perhaps that one right there, right? That one right there, right? There's going to be one somewhere around here, but I haven't drawn enough level curves of f to kind of make it clear where that is, and so on. So those are the candidates that I'm looking for. Those are the points that I'm solving for in this system of equations. Okay. All right, and as usual, once we have all our candidates, we're just going to plug them in. Among those candidates is going to be the biggest value and is going to be the smallest. So when I just plug them in, I'm going to get the biggest and smallest values of my function. All right. All right. You always think of it like this, right? If you let's say you have a classroom full of students, you want to know who's the tallest person in the class, right? Well, if someone brings up 5 students and says those are the candidates for the tallest person, right, among these 5 people is the tallest person, right? How do you tell which, who's the tallest person in class? You just take those 5, measure each of their heights, and the tallest of those 5 is going to be the tallest person in the class. All right, so it's the same idea with the candidates here. Okay, so before we do an example, the way I've drawn all my pictures here, right, for example, with this road, it's a loop that completely closes up on itself. A loop, in short, a loop, right? So a loop like this. So when I find my candidates, I plug them in and I'm done. All right. However, if I have a problem where the loop, where the road is not a loop, right? I want to find the highest elevation point of my drive, but I'm not driving in a loop, right? I'm driving from here to there on my map. Then I'm going to have my candidates, just as we talked about, solving these 3 equations. But I also have to consider the 2 endpoints. Okay? So those are like my boundary. You always need to consider the boundary if there is a boundary, right? And with the discussion above, we just happen to have no boundary because we're talking about a loop. So you don't have to worry about it. But in this second picture over here, there is boundary. So you have to include those as your candidates, because as usual, right? It could be, see, we're just looking for points where your car is horizontal. But if, let's say, you were driving uphill the entire trip, right? Even at the end of the trip, you're driving uphill, right? Then there's not going to be any candidates from this algebra up here, right? Because there's no place where you were horizontal. However, there certainly is a point where you are at your highest elevation, and that's at the end of your trip, right? But that cannot be captured by this kind of critical point analysis. So you always got to include your endpoints as separate candidates, if there are endpoints. Okay. All right. So one interesting thing here is now we actually, for the first time in a way, we're solving problems where there are no endpoints, right? We can solve a problem on a loop. Okay, so in fact, that's what we're going to do for our example. So let's find the biggest and smallest values that f of x comma y equals, and let's just do a kind of relatively simple function. This guy achieves on the circle of radius 3 about the origin. Okay, so this is one typical example of a Lagrange multiplier problem. Okay. Oh, by the way, this lambda, sometimes that's called, the technique is called Lagrange multipliers, and that refers to the lambda. All right. Okay. So in terms of the picture, this circle of radius 3 about the origin, right? This description here is equivalent to what we've been talking about. That's like our road, right? So we're interested only in this this road, okay? And because it's a full circle, there's no boundary to worry about. All right. Okay, and again, we don't care about how f behaves here, or here, or here, or here, or here. We only care about how f behaves on the road, or on the circle. Okay, so how do we do this? Well, we have our f. That's the function that we ultimately want to find the maximum or minimum of. We need to fabricate a function g such that the circle of radius 3 about the origin is a level curve of g. All right? So this is where we kind of need to have experience thinking about level curves, or kind of working with equations of functions and what their level curves look like. But for a function like g, a simple function would be g of x comma y equals x squared plus y squared. Okay. So if I use this particular g of x comma y, then our circle is the 9-level curve of G. Okay. All right, so our circle is a level curve of G, right? And it's the 9-level curve because what is the 9-level curve of G? It's where I plug in 9 for the G. And so that's going to be 9 equals x squared plus y squared. And 9 equals x squared plus y squared is exactly circle of radius 3 about the origin. Okay. So our circle is a 9-level curve of G. All right, so what does that mean? That means we need to solve gradient f equals lambda gradient g, where lambda is, again, unknown. And so that's kind of looking for the horizontal points. And we need to solve, and we need to be on the curve, right? So we need g to be of x comma y. So if we're looking for x comma y, I should stick those in there. Equals 9. Okay. All right, and that gives me my 3 equations and 3 unknowns. All right, so let's actually do this. What's gradient f? So f is x squared y. So gradient f is going to be, 2xy, comma, derivative with respect to y is just x squared. Gradient g is going to be, g is x squared plus y squared, so gradient g is going to be 2x, comma 2y. All right. Okay, before I continue, notice I always say we're looking for a function g, right? There could be many different g's that you choose, right? I chose this particular one, x squared plus y squared, because it's a nice, simple function. But you have a lot of options, right? So you could do g of x comma y equals x squared plus y squared plus 10, right? That would work just as well, right? As long as your circle is a level curve of the function that you discover, you're all set, all right? The difference is if I use x squared plus y squared plus 10, then I have to note that I'm not interested in the 9-level curve, right? I'm interested, in that case, in the -1 level curve, okay? Because the -1 level curve would be -1 equals x squared plus y squared plus 10. And so that's the same as x squared plus y squared equals 9. Okay. All right. That's a kind of a silly modification, but I could also do g of x comma y equals x squared plus y squared, whole thing to the 10th. I could do that also. All right. In that case, I would be looking for, again, a different level curve, but my circle would still be a level curve of G. Okay. All right, so that's a small note here. So it's possible that the way you do the problem could be slightly different from the way someone else does a problem in that they use maybe a different G. Okay. Also notice that where is my gradient G equal to 0? It's only at 0, 0, and that's definitely not on my circle. Remember, you really, really need to make sure gradient G is not 0 on your curve. Okay. So there's a lot of small mistakes that you can make in this process that can cause you to miss some of the critical points, in which case, of course, you could very easily miss the actual max or min that you're looking for. All right, so what are the equations that we actually need to solve? We need to solve gradient f equals lambda gradient g. So that means f sub x equals lambda g sub x. F sub y equals lambda g sub y. And again, g equals 9. Just in a shorthand, that's what we need to solve. And in terms of the actual numbers, that's going to be 2xy equals lambda times 2x. So that would be 2xy equals lambda times 2x, right? X squared times equals lambda 2y. X squared equals lambda times 2y. And then the last one, g equals 9, is x squared plus y squared equals 9. All right, and you can see that literally means we want x squared, y squared on the circle. Okay, I keep on emphasizing this one because it's very common for people to forget this last one. All right. Okay, and from here on out, it's purely algebra. We're no longer in the realm of calculus in a way. We're just solving algebra, solving for x and y, and lambda. Well, we don't really care about lambda. Sometimes you can solve x and y without having to find lambda, but probably I would say most of the time you will find lambda through the process. All right, but we don't care. We actually don't really care about lambda. Okay, so now it's just purely algebra. And here's the thing. You need to be very, very, very careful with the algebra. Again, it's very easy to miss a critical point when you're sloppy. All right. So, for example, let's actually do this one. Sorry, the first equation says. So I'm gonna number these. 1, 2, equation 3. All right. So let's look at equation 1. And again, this kind of algebra, these are nonlinear problems, right? This is not a linear system of equations. So there's no fixed algorithm that allows us to solve this. In fact, if the problem's nasty enough, if the kind of x's and y's have nasty enough interaction, we're not even going to be able to solve these by hand. All right? Maybe you use a computer or something. But there is no set algorithm. You're just going to have to take each problem individually and look at the individual equations to see what you can do with it. Every problem will be different. The algebra for every problem will be different. Okay, so just make sure you're comfortable with the algebra, because if you're not going to be able to find the critical points. Okay, so what does number 1 say? Number 1 says 2xy equals 2 lambda times x. All right, let me simplify that. Let's get rid of the 2's. That's xy is equal to lambda x. Okay, so here's a pitfall. Very frequently, people will just say, okay, cancel the x's. That means y is equal to lambda, right? But you better not do that, because you're only allowed to cancel the x's if x were non-zero, right? It could be that x was 0. For example, it could be x is 0, y is equal to 10, and lambda is equal to 7, right? Then definitely y is not equal to lambda, right? So you can't just willy-nilly cancel things, right? So if you see this, there's 2 ways to kind of write this out. You can say either x equals 0, or if x is not 0, right? If x is not 0, then you can cancel for sure, right? Because if x is not 0, you can divide by x on both sides, all right? Or y equals lambda. Okay, so that's probably a good way to kind of reason this out. Okay, so just be careful. Whenever you divide by something on both sides, make sure you account for the fact that that thing might have been 0. And if that thing was 0, you were not allowed to divide. Okay, so that's why the either or, right? If x were 0, then we would not have been allowed to divide. But if it's not 0, then we can divide. And then we can conclude y equals lambda. Okay, but luckily, a lot of the times, this case, for example, this x equals 0 case, makes things very easy for us, because x equals 0, right? When things are 0, often things are helps out in terms of solving equations. So let me deal with the x equals 0 term, in fact, right now. So when x is 0, so essentially now we're splitting this into two problems, right? If x were 0, then we look back at our equations, and we can see the third equation tells me, so in this case, equation 3 tells me, if x were 0, then y squared equals 9, all right? Which tells me y is equal to plus or minus 3, right? Which means I have 2 candidates from this portion of the problem. So I've got the candidates 0, 3, and 0, minus 3, all right? So if you had forgotten this part of the problem, you would have missed 2 candidates. And if your maximum or minimum happened to be there, then you would have just missed it. All right. Okay. So anytime you divide by something on both sides, better be careful. All right. And if you want to kind of avoid that mistake, one thing you can do if you want to be really disciplined about it is anytime you feel like you want to cancel, don't actually cancel. Throw everything to the other side. So this is the same as xy minus lambda x equals 0. And then you pull out the x's x times y minus lambda equals 0. And then we're all used to, in a way, when we see this, that we have two solutions, x equals 0 and y equals lambda. All right? So you could do that if you feel like you might make a mistake. All right, in any case, now we got to go back to y equals lambda. Okay? So you got to cover all the cases. So if y is equal to lambda, then let's look at equation 2. So equation 2 tells me x squared is equal to, y is lambda, so we've got 2 y squared. All right. Okay. Well, if x squared is equal to 2y squared, I can plug this into equation 3, and that'll tell me that 2y squared plus y squared is equal to 9, which tells me 3y squared equals 9, which tells me y squared is equal to 3, which tells me y is plus or minus root 3. Okay. Okay. So we've got y equals plus 3, and we've got y equals minus 3. What is x? Well, let's see. We have x squared equals to 2y squared. And so that tells me x squared equals 2 times plus or minus root 3 squared. So that's just 3. Okay. Just plugging in plus or minus root 3 for that y squared up there. All right. Okay. And I'm being very, very careful here because that means x is equal to plus or minus root 6. It's very easy to forget this plus or minus here. Right? Okay, so ultimately from this portion of the problem, I get 4 critical points, right? I get the critical point where x is root 6 and y is root 3. I get the critical point where x is root 6, y is minus root 3. I get the one where x is minus root 6, root 3, and then finally minus root 6, minus root 3. Okay, so ultimately I have 1, 2, 3, 4, 5, 6. 6 critical points, or 6 candidates for my max and min. All right, so that's the kind of Lagrange multiplier portion of the problem. I have no boundary, right? The circle has no boundary. And so I'm just going to plug in all 6 of these points. Kind of brutal. I have to plug in a whole bunch of points, but the good news is you don't have to use your brain, right? You just plug in. Right? That's what we're always looking for. Get to a point where you don't have to use your brain, right? So here we have f of x comma y was x squared y, and now we just plug in all of these candidates, right? So f of 0 comma 3 is 0. F of, I'm doing all the critical points roughly in order, minus 3 is 0. F of root 6 comma root 3 is 6 root 3. F of root 6 comma minus root 3 is minus 6 root 3. F of minus root 6 root 3 is 6 root 3. And f of minus root 6 minus root 3 is minus 6 root 3. Okay. So let's see. The maximum height that our function achieves on the circle of radius 3 about the origin is going to be at root 6 comma root 3, and the height is going to be 6 root 3, and also at minus root 6 minus root 3 minus 6 root 3, its height is going to be the same, of course, and then the absolute minimum is going to be here and there. Okay, and it's of course, perfectly legal to have multiple absolute max and mins, because you could, for example, on a drive, right? You could be at the same elevation at multiple locations on your drive. Okay, so that's it. That's the core idea behind Lagrange multipliers. So let me talk about a few things. Before we do that, notice I didn't actually bother to write down what lambda was in my computations when I found x and y's, because I don't care, right? I don't care what lambda is. I'm only looking for x and y, right? Okay, so a couple things. If I modify my problem so that I'm looking for, let's say, the same function, right? But I only care about find max, absolute, max, min of f of this guy, on the upper semicircle. Center 0, 0, radius 3. Then we would be only looking at this guy right there. All right. In which case, well, what's the upper semicircle? That's going to be where y is bigger than or equal to 0. All right. So we actually do the problem in the exact same way. We get to the same critical points that we found, right? The same 6 critical points, except because we only care about the upper semicircle, which is y bigger than or equal to 0, we throw away all the candidates where y is less than 0. All right. So we would get the same candidates, but we would toss out this guy, and we would toss out that guy. All right. Okay. And because this region now has 2 boundary points, we have to include them as candidates. All right. So this is minus 3 comma 0. That's 3 comma 0. So we would have to plug them in into our function. It just so happens that this particular functions for this particular, oh no, they weren't. Okay. It was 0, 3, not 3, 0. So you would have to additionally plug in these 2 points. All right. So you better not forget them because, again, the maximum or minimum could have occurred there. All right. So make sure you're very aware of what your region actually is. Does it have a boundary, right? And make sure when you're plugging in your candidates or when you're finding your candidates, make sure you're tossing out the ones that don't satisfy your condition. All right. Let me do another problem. So let me do a problem from one variable calculus that we actually talked about in 15.7. But let's do it natively in a way using Lagrange multipliers. So natively in 2 variables. So we have a rectangular fence that we want to build. We have a certain amount of building material, right? 60 meters of fencing, let's say. And so since we have 60 meters of fencing, we know that 2x plus 2y is equal to 60, right? And we want to maximize the area enclosed by this fence. So area equals xy, find max area. Find dimensions that give max area. Okay, so rectangular fence. The perimeter is 60 meters. We want to find the dimensions that gives us the max area. So completely out of one variable calculus, right? And in one variable calculus, the way you would have solved this is you would use the 2x plus 2y equals 60 to write, for example, y in terms of x. That would remove all the y's from the problem. You would have then a of x equals something in terms of x. And then take the derivative of a, search where it's 0. And you're pretty much all set, right? Consider the endpoints, of course. But now we're going to do it natively using Lagrange multipliers. So instead of converting everything to a of x, right, we're just going to work natively with a of x comma y equals xy. All right, so that's the function that we want to optimize. And now we have our condition. It's often called constraint. All right, and in fact, a lot of times instead of saying Lagrange multipliers, people say you have an optimization problem with a constraint, right? And the constraint is that, in this case, 2x plus 2y equals 60. In the previous problems, the constraint was that we were on the road, right? Okay, so our constraint is 2x plus 2y equals 60. So another way that's often written is we want to find the maximum of a of x equals x times y, subject to the constraint 2x plus 2y equals 60. All right. Okay, so this constraint, essentially, the formula for the constraint is gives me that g function that we've been talking about. All right, so I have my a of x comma y equals xy. This guy here is going to give me my g function, and in this particular example, probably the easiest g function I could think of is 2x plus 2y. Okay, this works because 2x plus 2y equals 60 is my 60 level curve of G. All right. So that's what I'm looking for, right? I want this equation here to represent a level curve of the function G. And I've confirmed it's the 60 level curve. All right. Okay. And again, a gradient G is 2 comma 2. Right? It's just a constant. And so it's definitely not 0 on our level curve, because it's not 0 anywhere, in fact. All right. Okay, so let's do our Lagrange multipliers. So we want to solve a sub x equals lambda g sub x, a sub y equals lambda g sub y. And we want to be on the curve, right? So G equals 60. All right. All right. Of course, this is shorthand. I should be putting the xy's, right? xy, 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 x comma y. So we're solving for x and y. Okay. So in this particular problem, a sub x is equal to y. A sub y is equal to x, because our function is just x times y. And so we end up having to solve y is equal to lambda times 2. X is equal to lambda times 2, right? Because gradient g is just 2 comma 2. And g equals 60 is 2x plus 2y equals 60. Right? It's always going to be kind of represented by the constraint. Okay. All right. And in this case, the algebra is super straightforward. 1 combined with 2 tells me that x is equal to y. All right. So again, right? I've done the algebra in this problem very different from the algebra from the previous problem. Every problem is going to be different in terms of its algebra. All right. Okay. It tells me x equals y, and then now combine this with 3. So 3 tells me, because x equals y, that tells me 2x plus 2x is equal to 60, which tells me 4x is equal to 60, which tells me x is equal to 15. And if x is equal to 15 and x had to be y, that means y is equal to 15 as well. All right, so that gives me my candidate from the Lagrange multiplier portion of our problem, 15 comma 15. Okay. All right, now, is there a boundary to our problem? Let's see. So we were interested in 2x plus 2y equals 60, right? The perimeter of our fence had to be 60. We're building an actual physical rectangular fence. So x and y cannot be negative. So x has to be bigger than or equal to 0. Y has to be bigger than or equal to 0. And so if we think about this, there's many ways we can kind of analyze this. But one way to think about this is 2x plus 2y equals 60. That's a line, right? That's the same as x plus y equals 30, which is a line that passes through 30 comma 0 and 0 comma 30. So it's going to be that line right here. Right? And we're interested in x bigger than 0, y bigger than or equal to 0. So we're only interested in the portion of this line between here and here. Right? The line extends infinitely, but we're only interested in this portion right there. Okay, so this is a Lagrange multiplier problem where we do have boundary points. And so we do have to consider them as candidates. All right. So the boundary point on the left is it's at height 30, x is 0. So 0, comma 30. That's another candidate. And the other one is 30, comma 0. Right. That's my right endpoint. Okay. All right, so ultimately, what do I have to plug in? I have to plug in 15 comma, I should check, right? Is 15 comma 15 actually in this blue segment? Yes, it is, because it's actually right there. All right, if it wasn't, we throw it out. Okay, in any case, we plug in all the values, and then the biggest is the max, smallest is the min, right? So A of 15 comma 15 is 225. A of 0 comma 30. Well, this is kind of obvious, but we should go through the motions, right? 0. A of 30 comma 0 is equal to 0. So that's going to be our max. All right. Okay, so that's really nice. It's a very nice way to do this problem because in a way, this problem is natively a two-variable problem, right? You are trying to build this fence and you have two parameters. You can have the length of the fence and the width of the fence. So it's natively two-variable problem. And so we've done it kind of as a two-variable problem. We've been, all through the problem, we've been looking at A as a two-variable function. All right. Okay. By the way, I think maybe people will look at these two and say, this is silly. Obviously, you can't have X and Y be 0 because obviously your fence will be 0 area. But we can easily modify this problem so that you do have to consider the endpoints, right? I could easily modify this problem so that the maximum is actually on one of the endpoints. And then if you're not considering the endpoints, you're going to miss it, like maybe on an exam or something, right? So easy modification. If I said, for example, for this particular fence, right, for whatever reason, I need one of the lengths, let's say the X length, I need this to be bigger than or equal to 20. Right? Because it needs to fit whatever, something in there. That's 18 feet long, right? So one of the sides has to be length 20, let's say X. So what that would, how that would modify the problem is that now instead of, let me just redraw it down here. Now instead of being interested in the line segment between here and here, where that's at height 30, and this is at 30 here, I'm only interested in X bigger than or equal to 20, right? So I'm only interested in, if 20 is right there, I'm only interested in this portion of the line segment. The previous critical point I found was at 15 comma 15. And now it's outside my region, right? It's outside my region of interest. So I wouldn't even plug it in. I'd toss it out as a candidate. And now you can see the only two candidates I have for the biggest possible fence is going to be this endpoint and that endpoint. So the maximum is going to be at the endpoint. So you better check the endpoints. All right. Okay. So this gives us our alternative to parametrization. So all those problems from 15.7, you can go back and do them all with Lagrange multipliers, right? So the problems where we wanted to find the maximum of a function inside the triangular area, right? The inside part is the same, right? What we called part 1 in 15.7, that's the same. You still search for gradient f equals 0, right? But the boundary parts now, instead of having to do a parametrization, you can do them with Lagrange multipliers, all right? So here you can use parametrization or Lagrange multipliers. Okay, sometimes one will be easier than the other. Depends totally on the structure of the problem. All right. Sometimes you won't even be able to parameterize because it won't be obvious how to parameterize. Right. If for example, one of the boundary curves of a problem like this is xy squared plus square root xy equals x cubed y plus y, right? you're not going to be able to parameterize this. So you're just going to have to use Lagrange multipliers, right? But on the other hand, sometimes it's super straightforward to parameterize, right? Like the problem here, maybe. You just have a horizontal line segment here. So you would parameterize this just with x comma, y would be a constant, whatever height that guy's at. And then almost instantly you have a one variable calculus problem that you can very easily solve. So totally depends on the problem, which technique which technique might be better, but you can always consider either of them. Okay. All right. So in this particular example, you would have, if you did it, no matter what, you would have to do, the inside part, gradient f equals 0. You would have to do for example, Lagrange multiplier problem here, here, and there. Okay. All right. If our region was something like this, right, 15.7 type problem. You would have to work the gradient f inside, but on the boundary, you can parameterize this portion of the circle. You can parameterize that line segment, or you can do Lagrange multipliers, right? 2 Lagrange multiplier problems, okay? Or again, you can mix it up, 1 Lagrange multiplier problem, 1 parameterization problem, whatever you're comfortable with, all right? Okay. So all of this we've been talking about has been with functions of 2 variables. But if we look at functions of 3 variables, we can now solve problems that we couldn't solve before at all, right? So if I had a 3 variable problem, well, first of all, the idea is completely the same. Gradient f equals lambda gradient g. G is supposed to represent your, the level curve, a level curve of g is your constraint. And you solve the same looking system of equations, all right? But here, look, we can do an example. We're not going to do the complete example, but let's say I want to find the maximum of, find absolute max min of f of x comma y comma z equals just whatever, x sine y z, right? On the sphere with center the origin and radius 4, right? We can actually do that now. Before 15.8, we wouldn't know how to do it, right? But now we can, because this is a Lagrange multiplier problem. We're trying to find the max and min of a function, and we have a constraint. The constraint is that we are only interested in points on the sphere, okay? And the sphere with center 0, radius 4, we can write that as x squared plus y squared plus z squared equals 16. And so our function g of x comma y, a nice convenient one, would be x squared plus y squared plus z squared, all right? And our sphere is the 16 level curve of g. All right, just to make sure, right? We always have to, we need to make sure g actually represents, the level curve of g actually does represent what it's supposed to, okay? All right, and now we can solve the problem. That's it. Now solve. fx equals lambda gx. fy equals lambda gy. Fz equals lambda gz. So the only difference is now we have to have this gz term. And then the last one is we're on the sphere, right? So x squared plus y squared plus z squared equals 16. Okay, 4 equations, 4 unknowns. We expect this to have a decent number of solutions. All right. Okay. So just think about, how you would have done this previous to 15.8, right? Probably you would have to do some sort of thing where you get rid of the z variable, right? Where you write z as square root 16 minus x squared minus y squared, plus or minus, of course. So you would have to actually split the problem into 2 pieces. Z equals plus that and z equals minus that. So already you can see, it's going to be a pain. So you first have to do that, And then once you have z equals something in terms of x and y, that means you can replace all your z's with x's and y's. And then you would have a two-variable problem. But your two-variable problem would be over this region down here. All right, so it would be a problem from 15.7. Okay, so you could solve it previous to 15.8, but it would be a huge pain. You have to solve two problems, right? Convert it to two variable problems from 15.7, right? And then, of course, for each of those two variable problems, there's a boundary, right? The circle. So a lot of work. Here, we just do one Lagrange multiplier problem. The sphere itself has no boundary, so we don't have to worry about any boundary points. Okay. All right, a nice fun mathematical fact is that if you have a region that's the boundary of something, then it itself has no boundary, right? So the sphere of radius 4 at the origin, it's the boundary of, so x squared plus y squared plus z squared equals 16 is the boundary of x squared plus y squared plus z squared less than or equal to 16, right? It's the boundary of everything inside a ball. And so it has no boundary because it's the boundary of something, all right? So it has no boundary. Just a fun fact. Okay, by the way, again, all the examples I've done, our functions have been differentiable, everything has been cool. If you do have points where your function is not differentiable, where there's problems with your function, you need to include those as critical points, all right, or as candidate points. Okay. So at this point, before we get into our next really major topic, I can mention that, remember way back when there was a section in the book, a mini section, that talked about the formula for the distance from a point to a line, right? What's the distance from this point to this line, right? And later on, there was a section when we learned about planes, there was a mini section in the book about the distance from a point to a plane. Right? What's the distance from this point right there? How far is it from the plane? All right. So we can actually solve that now. I'm not actually going to do the whole problems. I'm going to leave the one with the plane to you, but I can start out, let's say, doing the line problem. All right. So if we had a line, let's say y equals, let's just do it in general, mx plus b. All right. And let's say we have a point a comma c. All right. How far, so here we're going to get a general formula for how far this point is from the line. All right. So in effect, what does the distance from a point to a line mean? It means what point on the line is as close as possible to the point a comma c. All right, we want to find the point here that's as close as possible to a comma c, and that distance is the definition of the distance between the point and the line. All right, so we want to find the minimum distance, right? So we're looking at the distance to a comma c, but we only care about points on the line. So that's our constraint. So we have a Lagrange multiplier problem. Right? So we're working with the distance function, but I'm going to work, remember way back in calculus, one variable calculus, when you work with distance functions and you want to do optimization with distance functions, what you can do is solve the same problem with distance squared instead of the distance. And that makes your computations a lot easier because you don't have square roots. Right? So I'm going to do exactly that. I'm going to work with the distance function, dx comma y, the square of the distance function, is going to be x minus a squared plus y minus c squared. This represents the distance squared from any point to a comma c, right? We're only interested in points on our line. Okay, so we have a constraint. y equals mx plus b. We're only interested in points on the line because we want the point on the line that's as close as possible to the point. Okay? And that, again, that distance is by definition the distance from the point to the line. Okay? All right. And again, we want to find the minimum. Minimize d subject to this constraint, right? So immediately, Lagrange multipliers, right? I'm going to represent the constraint with g of x comma y equals y minus mx, for example. Okay, so in which case y equals mx plus b is the b level curve. Okay. All right. Again, because if I stick b in here for g, I'm going to get y equals mx plus b. All right. Okay. So now we just do the Lagrange multiplier procedure. D sub x is equal to 2x minus a. D sub y is equal to 2y minus b. I guess I'm using c. G sub x is equal to minus m. G sub y is equal to 1. Right? And so my system is going to be 2x minus a equals minus lambda m. 2y minus c is equal to lambda. And then y equals mx plus b. All right? And here we're looking for x, y, and lambda. M, a, c, and b are all constants. All right. This problem here is somewhat interesting in that what is the endpoint? Well, we're interested in the entire line, right? We're interested in the entire line. And so this is one example where we have an infinite region. Okay, so when you find your candidates, the Lagrange multiplier candidates, which is actually going to be this one right there, you're going to have to plug that one in, but you're also going to have to consider what happens as you go out out towards infinity out there and out towards infinity out there. All right. So you always have to say something, right? So if this was on an exam, you would say something like, you would either do the analysis, right? Or you could say something like, well, as I move farther and farther along this line, my distance to a comma c definitely gets farther and farther, right? So it's going to infinity. So it's definitely not going to be, going to infinity is not going to give me a minimum. And same thing going the other direction. Okay, so you have to make some argument. You always have to do some consideration of the boundary if there is a boundary. Okay, so in this particular problem, because we're talking about the distance function, we can use this intuition that, of course, as you go out further and further and further along this line, you're getting farther and farther and farther away from a comma c. So your distance is actually going to infinity, and so certainly you're not going to have anything to do with a minimum out that direction. Okay. And so your minimum is actually going to be the Lagrange multiplier point that we find down here with the algebra. Okay. All right. So one fun thing for you to do, I'm not going to do the rest of this problem. Probably a fun thing, a good exercise for you to do is to actually solve it and then confirm that this point, that the answer is actually perpendicular. So if I drop a line from a comma c down to my answer, it's going to be perpendicular to the line. All right. And another fun exercise is to do exactly the same thing for a distance between a point and a plane. Pretty much the same problem, except it's a 3-variable Lagrange multiplier problem. And then you can show that when you drop the perpendicular down to the point that is actually represents the minimum distance, that it's going to be perpendicular to the plane. Okay. All right, our final topic. This has gone pretty long, but there's nothing we can do about that. Lagrange multipliers is it's a totally new concept, and so it naturally takes a bit of time to discuss. All right, so our final kind of mini topic here is two constraints. Obviously, you can have more, but let's restrict ourselves to 2. So 2 constraints. So what if we want to optimize f of x comma y comma z, but we have 2 constraints, all right, with 2 constraints. Okay, so first of all, I'm talking about 3 variable functions with 2 constraints, because if you have 2 constraints, that's 2 equations. We're going to be talking about, essentially, that's going to be optimizing, finding the maximum minimum of f on a curve in space. So we're now trying to find the maximum minimum of f we're trying to find the point on the curve in space that maximizes our function. All right, and a curve, 2 constraints is going to give us a curve, because we said essentially each constraint is an equation. You've got 2 equations in space, so 3 dimensions. 3 minus 2 is 1, so that represents a 1-dimensional thing. So 2 constraints in 3 dimensions essentially means you're finding max min of a 3-variable function on a curve. Okay, so normally you wouldn't talk about 2 constraints in the plane, because 2 constraints in a plane means 2 equations in a plane, which means, well, plane is 2-dimensional, minus 2 is 0. So typically that's going to be 0-dimensional. So you're just trying to find the maximum of a function on a 0-dimensional region. 0-dimensional region are just points. And so if you want to find the maximum of a 2-variable function at a bunch of points, you just plug in those points. All right. So this only makes sense, this type of problem really only makes sense for 3 variables, 4 variables, 5 variables, and so on. Okay. And of course, for 4 variables, you can talk about problems with 3 constraints, and they would be interesting. 10 variable problems, you could talk about problems with 7 constraints, 8 constraints. Those would still all make sense. All right. Okay, so how do we work these guys? So let me do this very much with the pictures. So let's say we have a function f of x comma y comma z. Let's say our constraints are represented by 2 planes. All right. So we want to find the max or min of f, but we demand that we're only interested in points x comma y comma z that are on plane number 1 and plane number 2. All right. So 2 constraints means you need to satisfy both conditions. All right. So you're on plane number 1 and plane number 2. So for example, let me call this guy plane number 1. This guy's plane number 2. Okay. And if we have to satisfy both, that means we're on the intersection of these 2 planes. Okay. So we're doing an optimization problem. We're finding the max and min of f, but we're only interested in points on this red line segment. Right? And again, this red line segment, or this red line, if we want to do an infinite version of this, right, lives on plane 1 and it lives on plane 2. Okay? All right, so we're just going to discuss this idea very, very quickly, but because it's roughly the same, right? We want to look in directions tangent to this line or this curve. We only are interested in d sub u f equals 0 for u tangent to the curve. All right, so we're only interested in directions like this. Okay. All right, or we're only interested in finding where the directional derivative is 0 in that direction. Okay. All right. Well, let's look at these 2 conditions, or these 2 constraints. If constraint number 1 is represented by the equation, is represented by a level curve, let's say this is a 10 level curve of g. All right, and let's say equation 2, which is this horizontal plane. Let's say this is a 5 level of h, okay, of x comma y comma z, 3 variable now, of course, x comma y comma z. All right, then let's look at the gradient of f and gradient of g. So gradient of g is going to be perpendicular to my level, so it's going to be this direction, gradient g. Okay, gradient of h and gradient g. So gradient of h is going to be in that direction. Or the opposite, but you know, that doesn't really matter too much. Okay, now we want to find places where d sub u f equals 0, where u is along the curve, which means, again, gradient f dot u equals 0, u along the curve, right, tangent to the curve, which means we want to find places where gradient f is perpendicular to the curve, right? Okay, but what are the directions perpendicular to the curve? Well, if you look at this arrow here, perpendicular to it, there's, I'm going to draw it down here. So if this is my tangent to the curve, right, so my curve is in this direction, then the direction perpendicular to it, there's a whole actually plane of directions, right? So let me draw it a little kind of better in terms of the perspective. So this is the point of interest, and the plane which is perpendicular, maybe let's draw it like, okay, sorry, roughly the same. Oh, let me draw the arrows then. Perpendicular to the curve. So here, here, here. There's an infinite number of arrows, a whole plane's worth of arrows perpendicular. All right. In contrast to our previous situations where there was only one direction perpendicular to our curve in the 2-dimensional situation and to our surface in the 3-dimensional situation. So gradient f could be in any of these directions. All right. Okay. Well, it just so happens that if we think about this, gradient g and gradient h are both in the directions, are both in this plane that's perpendicular to our direction of motion. All right. So for example, gradient g might be here, gradient h might be here. Okay. So if f is to be perpendicular to the curve, it has to be on this plane. This plane can be, all vectors on this plane can be written as a linear combination of gradient h and gradient g. All right. So that's essentially tiny bit of linear algebra. And so what we actually end up needing to solve is gradient f equals a linear combination of gradient h and gradient g. So lambda gradient g plus mu gradient h, where now we have two multipliers, lambda and mu. All right. Okay. So ultimately, our system of equations, so these guys are going to give me my, essentially, the idea is that these give me my critical points in a way. But of course, we still need to make sure we're on the curve, right? So we need g equals, I said it was a 10 level, so g equals 10. And h, I said, was the 5 level, so this should be 5. So that's going to be our system of equations. All right, so we have 5 unknowns, x, y, z, lambda, and mu, and we have 5 equations. 3 from this guy here, and then 2 more. All right, so these problems are going to be quite a bit of work, but now we can solve problems where we have really complicated curves in space, and we want to find the max or min of f on that curve. All right, or again, even higher dimensional kind of problems. Okay, so maybe an example would be we have the intersection of a sphere with or an ellipse, maybe to make it even more unpleasant, with a plane, right? So the intersection would be something like this. If this was instead of a sphere, if it was an ellipse, this would be kind of an oblong elliptical object, right? Might not be so easy to figure out a parametrization for it. How can you do it? How can you find a maximum of f on this region? Well, you can do Lagrange multipliers with 2 constraints, lambda and mu. All right? And again, as usual, we don't care about lambda and mu. We're actually solving for x, y, z. But sometimes you'll have to find lambda and mu as you solve for x, y, and z. So here's a really nice problem, or a problem that you might have to solve. Find the max mins, absolute max mins of f of x, y, z in the region bounded by or let me say in the region, yeah, or let me say in the region satisfying x squared plus, let's say, y squared over 16 plus z squared over 25 less than or equal to 1, and x plus y plus z, let's say, bigger than or equal to 1. All right. So what would this problem be? So you're doing a 3-variable optimization problem. It's over a region. The region is 3-dimensional because of essentially because of the inequality signs. And in terms of the picture, this first guy is an ellipse, ellipsoid, I guess. The second guy is a plane, or one side of a plane. And so essentially you're looking at something like, you're looking at an ellipsoid, but only a portion of it. So the portion of an ellipsoid that's cut by a plane. And you're interested in this inside of this region, right? The whole region, not just the boundary, because of the inequalities. All right. So what is this problem? This is a 15.7 problem, right? You're finding the max min of a 3-variable function in a 3-dimensional region, but the boundary of it is 15.8, right? The boundary of it is Lagrange multipliers, where your 2 boundary pieces is the upper part of the ellipse, right? The bottom part here is cut by the plane. And then you have the planar part, which is the bottom part right there, which fits right inside there. And so this is 15, you're going to have to do a Lagrange multiplier here and here. Okay, and when you do the Lagrange multiplier problems, each of these have a boundary. So this guy has the boundary being the circle, all right? And this guy here has a boundary. It's actually the same circle, so luckily you don't actually have to do 2. But these are boundary. So these you could do also as 2-constraint Lagrange multiplier problem. If you want, you could also parameterize, of course. Right? And your 2 constraints are, what is this region defined by? It's on the ellipse and it's on the plane. Right? So your G and H would be the equation of the ellipse, ellipsoid, x squared plus y squared over 16 plus z squared equals 1, and then the plane x plus y plus z equals 1. So satisfying both those conditions gives me the circle right there. All right. So this is a nice combo problem. Gradient f equals 0, Lagrange multipliers for the boundary, and then the boundary has the boundary, right? Well, the boundary has boundary in this case because you're splitting the boundary into 2 individual pieces, and each individual piece itself has a boundary. Okay. All right, so you can have some really interesting problems in this using, being solved by Lagrange multipliers. A lot of word problems can be done with this, but word problems as usual, you just need to convert it to the math. Look for the keywords of biggest, smallest, longest, shortest, and so on. And in terms of the constraints, right, look for words like you're only interested in points where this or that happens, right? That sounds like a constraint, right? You're building a fence, but you are only interested in fences where the perimeter is equal to this, right? That's a constraint, something like that. That indicates that you very likely have a Lagrange multiplier problem. Okay. All right, so 15.7 and 15.8, I've said this before. These are, if I had to choose one thing, which was the most important thing in the class, where you could forget everything else, well, you shouldn't, but if I were to choose, it would be Lagrange multipliers, or not 15.7 and 15.8. All right, so for sure you'll see both of these on the exam, maybe with multiple problems. In fact, it's probably even possible. I haven't written the exam, but it's probably possible to do the exam where it's all optimization problems, And through the optimization problems, I can test everything else, right? Because these optimization problems involve oftentimes understanding about planes, understanding about equations of surfaces, right? Understanding vectors, understanding the gradient, understanding the directional derivative, understanding the picture of Lagrange multipliers, which is the picture of level curves. So this kind of stuff can really test everything in the class up to now. All right. So make sure you're very, very comfortable with Lagrange multipliers with 15.7. Lagrange multipliers in particular, because it's something that's very, very new. And yeah, do as many exercises as you have time for. Okay, so next section is 16.1. That's going to be really light because we're going to be doing the really heavy stuff, start 16.2 and on next week.